Hi friends, we have already seen about what is meant by a random variable, the types of random variable and how they can be classified for their mean, variance and then moments. Now this comes as a continuation or in part 2 of the random variables. So having known what is meant by a random variable, we need to see where they can practically be put to use for. So when in practical life we are going to use random variables, how we can differentiate between them and which is the right distribution to opt for under what case. So that is what is going to be discussed in this video. Now the theoretical distribution, that is the random variable being put to use for theoretical purpose, can be broadly classified as two types. The first one being discrete distribution and the second one being continuous distribution. So what is meant by discrete distribution? A discrete distribution is one that takes finite number of values for its random variable, in which case we will be making use of summation as the mathematical operator. And how about the second one? It is the continuous distribution. What is meant by continuous distribution? A random variable, if it is going to take infinite number of values in a given interval, then you will be applying for a continuous distribution. And so to account for the uncountable number of values, we will be making use of integration as the mathematical operator. For this purpose of study, under the discrete distribution, the videos will be covering quantities on binomial distribution and Poisson distribution under discrete cases. And we will also be seeing under the continuous distribution the applications or the type for our exponential distribution, uniform or rectangular distribution, normal or otherwise referred as Gaussian distribution. Now, when a question is addressed to you in the question paper, they will not be specifying in explicitly whether the problem is going to be binomial or the problem is going to be Poisson in nature. So depending upon the situation in which it can be used, we will have to first fix whether it is a binomial and Poisson. So what is going to be the first guess which we can make to fix the binomial and Poisson, or like what are going to be the basic assumptions that can be done over here? Right, we'll see that first. Let n be the number of trials. So you do an action again and again and again n number of times, then or you repeat the action for n number of objects using n number of objects, then you call n to be the number of trial. If the number of trial is going to be very less, then you will be applying binomial distribution. What do we mean by less? When n is going to be less than 20 in count, so you are doing the action for less than 20 number of time, or you are doing it for less than 20 objects in your hand, then you will be applying a binomial distribution. But rather in the case when you have the number of entities to be more, so if it is going to be greater than 20, then it is best suitable to apply a Poisson distribution. Say if you are having a game which is being played by 10 children, and then you are going to see what is the probability that one of them is going to get success or not, or 3 of them are going to get success, or at least 2 of them are going to get success. In which case, since there are going to be 10 number of people or students or kids who are going to play the game, then we will be going for binomial. Say number, if you are going to see how many error are there going to be in a book that contains 500 pages, so you will have to turn for 500 pages to search for an error. So the number of time you turn on the page is going to be more in number. So how many time you turn on the page, so it is going to be again and again for nearly 500 times. So when an n becomes greater than 20, then it is best suited to apply Poisson. Now we are just gone for the case less than and greater than, but what happens to the sign like equal to 20? So what can we do at that position? we need to keep in mind here that when it is going to be 20 or in and around 20, like less than quantities like 19, 18, 17, or more than quantities like 21, 22 and 23 and so on, both the binomial and Poisson will give us more or less the same answer. So in and around 20, both the binomial and Poisson will work like they are like one and the same, and the answer will most probably be the same. So at what situations can we see this binomial distribution as a limiting case of Poisson distribution? So that is going to be the next thing of consideration. There are going to be three cases when I can see the limiting cases of a binomial seen as a Poisson. Now, as n tends to infinity, the number of trials become more and more and more. The number of trials is going to be more. Then obviously the binomial problem will be moving towards a Poisson problem. So for more number of trials, as n moves towards infinity, the problem will become more Poisson in nature rather than being binomial. The second condition is that as p tends to 0, what does p stand for? P stands for probability of success. So what is going to be the range of probability? Usually our probability is going to be a quantity that lies between 0 and 1. Probability is told as 1 when it is going to be a sure event, when you have a sure event, and the probability takes the value equal to 0 when it is going to be an impossible event. So I say probability moves towards 0. So what happens over here? We are considering the cases of impossible events. So or things that are going to be rarely happening. Then in such cases the problem will become more Poisson in nature. So for an impossible action or for a rarely happening event, we will be applying a Poisson distribution. So for a day-to-day activity or something that happens in our day-to-day life, like what you're going to be, the number of times you're going to go for a shop, or number of times you're late for a class, something of that sort which is going to be happening regularly, then that is going to be something which is going to be binomial in nature, because the probability of happening of the action is going to be more closer to 1 rather than moving to a 0. But say the case that someone is going to meet with an accident on road. So that is, meeting with an accident is not going to be something that happens daily or which is going to happen more frequently for one single person. Maybe it is the case where you frequently see it for the number of people in the road, but for considering one single person, you don't go and bump yourself again and again. In which case a particular person meeting with an accident is going to be something that happens rarely, or something like you have prepared so well and that you failing in an examination is going to be something like it is next to impossible, and someone is aiming a target at India, and that target is going to be hitting the place over here is going to be something which is rarely happening. So under all these kind of situations, we will be moving or we will be applying Poisson distribution. The third limiting case is one, what defines a Poisson distribution is going to be its parameter lambda. Lambda is also known as the mean of the Poisson distribution, but we don't know how to estimate the value of lambda. Then there is going to be a tricky way or quickie way where this lambda can be expressed as n times of p. N the number of times the action happens, and p the probability of success for each time the action happens. So when lambda equal to np or lambda tends to np, then we can use this Poisson distribution to estimate the data for our probabilities. And so this is going to be called as the three limiting cases, where you can treat a binomial problem to be more moving towards a Poisson or merging with one another. So dear children, please keep it in mind whenever you have the case that n is going to be in and around 20, your number of trials is going to be in and around 20. So either in this way or in this way with a shorter span of values, then binomial and Poisson, both of them will work in the same way. Now coming to the next thing, like there are going to be two types of quantity that has to be taken into care of. We always estimate what is going to be the probability of going to be greater than or equal to a, probability of x less than or equal to a, and probability of x equal to a. What are these and how are these referred to in problems generally? So now here is a case where x is going to be greater than or equal to a. So it takes a plus 1, a plus 2 and so on. So a is going to be the least value x can take. So this word or this kind of probability is referred by at least. So find the probability that it is going to be at least 3 values, at least 3 boys are going to participate, at least 10 people are going to go for the election, and so on. So when it is going to be greater than or equal to, a forms the smallest, the lower bound, then we refer it by the word called as at least. Next comes the word x less than or equal to a. So less than or equal to a. So a is going to be on top and then it is going to move like lower. So next one may be a minus 1, a minus 2, and so it moves in this way over here. So what happens over here? A now becomes the maximum value that random variable can take, or this is going to be the upper bound for all the datas, in which case what you call this is by the word at most. Okay, so whenever the question asks you estimate, at most 3 people do it, at most 10, so it is 3 or less than 3, 10 or less than that. So the word at most says that it is going to be less than or equal to. And next comes x equal to a. So there is going to be only one chance that x is going to take, and that is going to be nothing more than a itself. So you call it as exactly. So if these words occur in the question, please be careful. At least means you will have to make use of the inequality greater than or equal to. When the word at most appears, you will have to make use of the inequality less than or equal to. And whenever you have equality, go for equal to sign. Okay, so this will be more helpful for all the distribution that is going to follow over here.